Hi everyone, welcome to Seismic Data Processing course. So we continue our main processing. Today we have velocity analysis and NMO correction. In the previous lecture we understand the theoretical part of seismic velocity. So in today's lecture we are continuing our velocity analysis and NMO correction. Velocity analysis, so when we record the reflected seismic wave at different distance, different offset from the source, these reflections events appear as hyperbola, like that, on the seismic gather. To correct, to stack or add these traces together and enhance the signal, we want to flatten this hyperbola. So in order to stack all the traces, to make them in one trace, we have to flatten the reflections. Instead of this hyperbola, we want to stack them to make them flatten. So the velocity we choose to flatten is called the stacking velocity. It's different from the RMS velocity, root mean square velocity. Root mean square velocities represent the true geological subsurface, but this velocity is not always the true velocity of the subsurface. The stacking velocity will be equal to RMS velocity in case we have horizontal layer, but if we have dipping, it will not be the same. We have the semblance and offset and CVS. These are that we are going to see with this processing software. Just a minute. We have the NMO, normal move out concept, from the source and to the interface and back to source is called the move out. So if the distance is longer, the move out will be normal move out will be longer. So we have the time and distance is the distance from the geophone. If the source is back with the short time, you'll see this one in here, but if the longer is distance, the bigger is the NMO, the move out. The longer is the distance, the bigger is the NMO. So it depends on the receiver, depend on the distance from the interface and back to the receiver, you will have the bigger NMO. This is the concept of NMOs. This being the source, interface and back to receiver. Some of them will back with a shorter time, some of them will take a lot of time. So this is how we calculate the equation of NMO, the time. These are the second time that we are calculated after the hyperbola curve. We calculate the second time, the time after we need to correct, equal to the initial time plus the distance between the source and geophone and divided by the velocity. And here this is the true velocity. It represents the RMS velocity for the true subsurface geology. And we have the NMO correction. This is the correction that we did. So we calculate the NMO velocity, normal move out velocity within the hyperbola curve, and then we apply the corrections to remove the effect of the offset. So at the end we have the normal move out corrections time. This is the time per x, this is the time for per any distance within the geophone, and minus the initial time. So in here we will do within the processing software, we are going to pick the NMO velocity. It's the same called the stacking velocity. The purpose is this is the hyperbola reflections. We have to flatten this hyperbola in order to do the stacking. So we have the NMO corrections equation, the travel time curve. This is the travel time curve of the reflections of different offsets between source and receiver is calculated by using. So this is the travel time, the curved travel time, the initial travel time, and divided is the distance from the source to geophone divided by the V stacking velocity on NMO velocity. So for this formula, the NMO correction can be driven. So you have the T per X, this is the travel time at the last distance we want to cover, the initial time multiplied by X, the distance from the source to geophone, and divided by the V velocity square stacking velocity. So let's gonna go for browsing software. I provide this software for you in the previous lecture. If you don't know, just back to the previous lectures. We have Vistawin software. Okay, close this one, open. I also provide the data for you. You can check on the previous videos. Open this data. So the first we are going to pick the data for job flow and open a flow file. In here we are going to pick S20V ln.flw. I'm going to select this one. So these are the semblance and common offset stack and constant velocity stack, the one that we described in the lecture. So we have first to identify each one and put the data list. So if you have, this is the bin from central bin, I'm gonna keep it as default. And also we have the exponential, this is the gain exponential, we described in the gain lecture. I'm gonna keep it 1.7, so cancel. And we have the main, this is the parameter output scale factor, I'm gonna keep it 1. We have the deconvolution, this is the deconvolution, they have the deconvolution type, this is predictive deconvolution. We described that in the previous lectures. Also we have the spiking deconvolution and zero phase deconvolution. You can select spiking deconvolution and you can select the type of deconvolution that you want. And also we have this the band filter that we apply for low cut filter, high cut filter, and high truncation filters. This depends on if you need to cut the low frequencies or the high frequencies. And also this is the main, this is the output scale factor. And you have to make sure all of these with the green color. If you have a red color, that means this step is not processed. So you have to click on this step and correct if you need to set the parameter. Otherwise, it's not going to work with you. So you have to make sure in this the constant velocity stack. You have to set the velocity stack and these corrections. So I'm gonna keep it now for as default. You can save your flow. Also, you can save a flow. And this is flow command parameters, and this is delete command if you need to add create this is create a flow command links. So after everything's in here in a green color, you should go for go. This one will execute the this process, so you know this process is going well. So close this one, and then after we close also this one, save it, or you don't need to save. After we finish the job flow, go for interactive velocity tools, interactive velocity analysis. From here we have to select the last one we just saved. So we have CVS and semblance, CVS control, and these are three: short 20, short 20, CVS output, this is for the first one, and semblance output, and this is off stack output. So click OK, and now here we go. We select three type of common midpoint. We have 50, and also we have 100, and then we have 150. These are the three common midpoint. We are just selected from the flow, and go for picking velocity. You need to start picking. When you move your cursor, you will see you are highlighting the parabola reflections. So you can select this, the first one as reflections, and we have in here, this is the very clear reflections, this is the hyperbola reflections, and this is the very clear hyperbola reflections. Also we have the third one here, and also this one. Can highlight this one. Can check with display correction NMO gather. It will allow you to see if your reflections are flattened or not. You can see your reflections are flattened. So if you need to do the CMD at the common midpoint at for 100, you can do the same. You will see this automatically selected because you do the first one, and now you can edit on this one. For example, you have this one here, the second one, third one in here, we have the fourth one. Also, you have this one in here. So after you finish, select all of them. You can do one by one, and you can select them properly. You can go for display current velocity picking. So this allow you to see your picking, the reflections, the flattened picking within the time. And also we have in here the graph velocity view, and in here you can see this is a VRMS velocity, root mean square velocity is compared with the internal velocity and the previous velocity. We also have a 3D velocity view, so this you can check your 3D velocity view with time the x, the distance, and also we have this in here display the current velocity picking, and you have a 3D. So this is all you need to know about this lecture. So thank you for watching, and see you in the next video.